The Ben Heck Show is brought to you by Element 14, the electronic design community where you can connect and collaborate with top engineers from around the world. Join now at element14.com. Hello and welcome back to the Ben Heck Show.
Ben was telling me about a gamer in the early 80s that set the speedrun record for Dragster. However, there's some contention about that record.
Right, it's the oldest video game record that is still standing, and a modern speedrunner named OmniGamer has done a lot of calculations, and he doesn't think that original time of 5.51 seconds is possible. He thinks the best is 5.57 seconds. And he's done a lot of tests with emulation and spreadsheets, and it seems quite thorough, but the guy who runs Twin Galaxies asked me if I could do some analysis using a real Atari, just to make sure. And I was like, well, okay, I mean, I don't really care about high scores personally. I'm not a good enough player to care.
But it sounds like a really fun project to try.
Yeah, so it's a good excuse for me to build a RAM analyzer for the Atari 2600, like analyzing this bus with newer hardware, something I've always been interested in. So what I want to do is create a device, and when the CPU writes to the RAM, this external device will see that and make a copy of the data, and then it can put that data into another memory array that we can read with a microcontroller. And then if we get that RAM copier working in a future episode, the microcontroller could look at that RAM and then make decisions about how to best play the game.
This sounds cool.
Let's get started.
Amazing hacks.
Should we take it for a spin?
Inspired designs.
Imhotep's priests.
Regrettable acting.
No one seems to get it.
Each week, Element 14's The Ben Heck Show brings you innovative projects using electronics, engineering, and more.
Hey, look what came in the mail. It's an Atari 2600 Junior. This is the last official model of the 2600 to be released. These are actually pretty inexpensive to obtain, which is strange because you'd think this would be the rarest one. Of course, here, rarity means nothing. We'll take apart anything. I mean, I've taken apart the rarest console in existence, so after that, just all downhill. Like after Indiana Jones finds the Holy Grail, what else is he gonna do? He's gonna be like, my life is boring. Like, you know, if he finds a quarter in a payphone, it's gonna be like, so what? Of course, back in his day, it's probably like a dime to use a payphone because he was from the past. I used to be obsessed with this model because some of them have a single chip in them, which I hope this one doesn't actually, because that would not work for our purposes. But from what I remember about looking at them, I don't think this one does. And it's 3 chips, good. What's holding the circuit board in? Oh, it's tabs. So high tech. Why use a screw when you can have pieces of plastic doing the work for you? Ta-da! Oh boy, it's the classic Atari heat shield. Heat shield, come on. It's the classic Atari RF shield tabs, yay! There's the chip in question, dun dun dun. I just thought of a possible problem with this. If we have a cartridge plugged in here, it might be kind of hard to put the test clip onto the RAM. I'm sure we can figure something out though. This is all that was in an Atari. Not much at all. All right, so I've been working on some test equipment for the Atari 2600. I had some of these microchip pigtail cards laying around. This plugs into a development board that they sell that hooks up to their starter kits, of which I have many. And I've put on these Texas Instruments voltage transceivers. It's the TXB0108. And what this does, it has an 8-bit bus on either side, and you can put 2 different voltage rails on it. In this case, we're gonna have 5 volts and 3.3 volts, and then it will do automatic conversion for you. You've probably seen us on the show use just standard logic gates and buffers to do that, kind of hacking it, where we basically just feed the buffer with the lower output voltage so that when we put the higher logic into it, it comes out at 3.3 volts. For this, I wanted to do it a little bit more properly. So what I'm rigging up here is my primary test. I have these dip switches, like a bank of 8 dip switches. They have pull-ups on them, and then when you push the switch like this, it'll go low. And what I'm doing with this is I'm testing a couple things. I'm testing to make sure that the bus transceiver properly converts 5 volts into 3.3 volts. And then when I plug this card into a PIC development board, this particular port, R0 through R7, is the parallel master port, also the parallel slave port. And that allows us to do 8-bit read-write operations into the PIC32. It allows the PIC32 to interface with standard 6800 series logic, like a 6502 microprocessor, for instance. I've seen projects online where people have used PIC microcontrollers as UART transceivers. So they'll have their 6502, I think it was on 6502.org, they'll have their 6502 address the parallel port and put a byte into it, and then the microchip PIC will see that byte there and say, oh, I've got a byte. Actually, an interrupt triggers when the byte appears. And then once that interrupt triggers, the PIC will take it and put it onto the TX or RX bus out of the system. I think it would probably be bidirectional too, so you could also read bytes coming in. But all I want to do with this to scan the Atari's memory is send bytes to it. We'll have the 8-bit data bus coming in. I'll also have to hook up the address bus. But basically, this will act as a clone of the RAM, so it can monitor what the Atari is thinking, more or less. There is one other register we might have to think about, and that's the timer that's built into the Riot chip. We'll probably come to that later. But I think RAM would probably be enough to do the job here. All right, so I'm going to do a few more things, and then I can do a voltage test. All right, so I got this IC tester clip. Basically, the idea is you can squeeze it onto a DIP40 chip, such as this one, and then you have easy test points. The reason I got this was so we could hook this up to whatever Atari 2600 we wanted and just grab all the signals off of one of the chips, including power and ground and clock and address and basically everything. So I've been wiring this up. This is my PIC-tail connector for the PIC32MZ. I have some logic here which does an address decode. Basically, it only sends a pulse when we are addressing the RAM. And then I'm going to run the data and the address line through these 3.3 volt to 5 volt transceivers so we can knock it down to 3.3 volts for the PIC32. So the PIC32 can read it without damaging itself. What ports to use, I still don't know. I think I might have to wire this thing up again. I was looking at using the parallel master port in slave mode, which would make it a parallel slave port, but it appears to only work in 8 bits. But then I was looking at the timing diagrams of a 6502. Actually, I have that right over here. I could latch the address on the rising edge here and then wait a specified amount of time, which is TMSD, which is 200 nanoseconds, for the data write to be valid and then get the data line there. So basically, when I see this edge rise, which would be the result of these logic gates. So the output of all these logic gates, when that rises, I store the address, I wait 200 nanoseconds, well, probably more like 300 just to be sure, basically within this window here. And then I store the data bus, and I'm like, okay, so whatever I got off the data bus, I put into this address position in RAM, and that should give me a copy of the RAM. So we're talking about a 1.12 megahertz CPU, and it's going to be read by a 200 megahertz CPU. That sounds like overkill, but not necessarily, because the 200 megahertz CPU still has to do multiple instructions in order to read this. Although if we put this as an edge interrupt, the edge interrupt should trigger everything. So basically, when we see a rising edge, we jump into an interrupt, and then we get the timing, and then we exit the interrupt. So yeah, I've just got to do more wiring. So I had some problems using the PIC32 starter boards and the expansion board because the newer PIC32MZ chips didn't have compatible pinouts. So all of these pinouts, well, not all of them, but a lot of them are inaccurate. So I thought the fastest way to do this is just to grab the chip kit, which has pretty much all the I/O going out to headers, which makes it pretty easy to use. All right, here's my new plan for capturing the data and address bus off of the Atari 2600. All right, so we have this write clock, which we hooked up with some AND and OR gates. And every time that goes high, that means the RAM is being written. Now, there's different areas of valid data in this clock. The address is available immediately. So what we can do is we can look at that rising edge and use that to clock the address flip-flop. So we take the Atari bus side and we copy those 8 bits over here so that the PIC32 can read it. So that part's easy. That always happens right here. The data part's a little trickier because the data happens a little bit further in. So the data is not valid until about halfway through this high signal. On top of that, as we showed, there's a possibility of having a double write immediately in the RAM if you're doing an increment or decrement command. So we also have to not latch the data until a certain amount of time has passed. So what I figured out is that we can use a pair of hex D-type flip-flops in order to trigger the data address flip-flop. So here's what we do. So the flip-flops both have a clock and a clear. Now, if you pulse clear low, it clears out all of the outputs and makes them 0. What I did on each flip-flop is I put a high, basically I pulled up D1 on each flip-flop. So every time you clock it, that 1 will go boop to there, boop to there. It'll keep cascading down. So we can use that as a kind of counter. All right, so the trick was I ran our write strobe into an inverter. So we have two versions here. We have a data enable pulse, and then we have interrupt pulse. So there's two things that we latch. We latch when the data is valid, and then we also send a signal to the PIC saying, okay, the data is ready, now you can grab it. So here's our subclock we talked about before. We're using the subclock to actually drive these flip-flops. But if they're held in a clear state, the clock won't matter. It'll still all be 0. So we go 1, 2, and that's what we call the data load edge. So that's why we have the subclock going here. So once this is high, that means this flip-flop can work. Then it gets 1, 2 pulses. So the 1 goes here, then it goes here, and that goes into our data latch, see? So here's where the magic happens. So if that goes low again, this flip-flop is disabled. That's already been latched. And if there's another immediate write, like we saw with the increment decrement command, this goes high again, which means this flip-flop gets reset back to 0, and the same thing happens, 1, 2. So the same data is latched again, and then it gets latched again, which is good because when it's doing increment decrement, the first time it writes the RAM, it's the old value. The second time it writes the RAM, it's the new value. So basically this makes sure that it's always the last write that is valid. And then on top of that, we use the inversed write strobe to trigger the interrupt. So this goes low and this goes high, which means this flip-flop becomes active, and then we get 1, 2 clocks on it, 1, 2, and that gives us our rising edge interrupt strobe. So yeah, we count 1, 2, valid data, and then once we're done writing to the RAM, we count 1, 2, valid interrupt, and then that gives us a latched data and address that we know are correct coming off the Atari. So we're using this low-level flip-flop circuitry to ensure the data we're giving to the PIC is accurate. Because the PIC's fast, but it's not as fast as dedicated circuitry when it comes to detecting things like clock edges and cycles of a 6502 write. This should work. Hey Felix, I think I finally figured it out.
Awesome.
So I hooked up another one of these hex flip-flops. I realized we could do something. If we put a high signal on the first data input and just leave it there,
Okay.
and then if we clear the flip-flop, all of the outputs, all the Q outputs are low, right? Then every time we clock it, that 1 will propagate. So it'll go boop, then boop, boop. We could go all the way down the line. So, you know, the ones that are 1 will stay 1, but then these will move down the line. But that doesn't really matter because all we need is a rising edge. It doesn't have to be a pulse because we can detect a rising edge on the microcontroller. So what I did was I hooked up 2 of these flip-flops. So clear is active low on these flip-flops.
Okay.
So I hooked up the write clock through a NOT gate. So one of the flip-flops is cleared when the write edge goes low, and the other one is cleared when it goes high.
All right.
So basically we can count within the write clock and outside of it. That way we can count 1, 2, and that's when we latch the data. And then once the write is done, we count 1, 2, and that's where we send the flag to the microcontroller.
Do both of the flip-flops have this high coming in?
Yes.
Propagating? Okay.
So they're basically being used kind of like a decade counter. I think we could have used a decade counter, except for the flip-flops are much faster. So let's do an example. So the system's on.
Okay.
If you could help me find some data, let's try to find one of those double writes. Go ahead and stop it anytime you want. All right, zoom out, see what you can find. Well, take a look at a single. Oh, wait, we got a double and a single there.
Oh, I just...
Oh, no.
I lost it.
I wish there was a voice-activated scope,
All right.
you know, and you could say stop. Okay, looks like we got 2 singles and a double.
Yeah, pretty close to each other.
Hey, that'd be enough for a home run in baseball. All right, so we're clocking the flip-flops using the sub clock.
All right, what's the pink?
So the pink
signal?
is the sub clock. That's the 3.5 megahertz clock. The green in the middle is the write clock. That's the system trying to write the RAM.
Okay.
The cyan one, that is the output of the second flip-flop, and the top line is the output of the first flip-flop.
Okay.
So see right here, we count 1, 2, and there's a pulse, and that'll be our flip-flop, our octal flip-flop data latch, basically storing the data. And then when that goes low, it resets that clock. We count 1, 2, but this one doesn't get to count all the way to 2, so it starts over. Then again, we count 1, 2, and we latch the data again. So just like the RAM, the data will be latched into our output data flip-flop twice. And then it'll stay there, and then the second flip-flop kicks in, 1, 2,
Here?
3. Yeah.
1, 2.
Yeah, actually, we could probably do it faster than that. Let's try it one more time. I thought I had it in the right position. Let's see, so this is output of 2. Output of 2, run it again.
All right.
Anything?
Oh, yeah.
Yep, stop it there. Yeah, see how line 2 only rises once this is done with? So yeah.
And that line 2 will send a signal to the microcontroller.
That'll be the interrupt flag.
Okay.
Yep. So it'll latch the data twice, but that way it'll latch the old value, then it'll latch the new value, and then this thing will count. That line will go to 1, which is the output of the second flip-flop. But yeah, this should take care of the double issue, and it'll only write once, right? So basically all this is doing is it's counting 1 cycle, so the data is valid right there. And then once this goes low, it counts 1, 2 cycles, and then the data is valid to send to the microcontroller. And then a single will also work. See?
Yeah, see how that works.
Let's check one more thing.
All right.
There are occasions where it's doing 2 different writes in close proximity. That's why we want to send the data to the microcontroller as quickly as possible. All right, let's run it. Zoom out a little bit. Yeah, capture that. All right, see what we got. Yeah, see, these are pretty close together, but they're not that close together. Yeah, see, right there?
From here to there?
Yeah, from there. Why are you over there, cursor? So that's about the fastest that it could happen, and that's going to be... I'm so glad the cursor menu is covering up the thing that I want to measure. 32 microseconds. That's not that fast at all.
Okay.
Yeah, so that's about 1/100th the speed of our PIC32. I guess my point is, if we waited too long to store it back to the PIC, the other one might occur already. But as you can see, these are like the closest events that we can find.
Yeah, you want to make sure that we are able to read it before the next.
Yes.
Right.
Because the way the interrupt works this is a hardware capture solution, but ultimately the PIC32 is a software solution. Cool. So I guess the next step is to hook up these flags to the 2 clocks to load the flip-flops. Like load the address flip-flop and then load the data flip-flop. So we can load the address flip-flop right at the beginning of the write strobe. That's a no-brainer. Then we wait 1 cycle, then we load the data flip-flop, then we wait 2 cycles, and then we send the flag.
Okay.
So basically we're storing the address and the data using these flip-flop buffers. That way we know the data is valid. And then once we know all the data is valid, then we tell the PIC to read it. That way we ensure that we have valid data. Before we didn't know that. Okay, I've got the system hooked up with the new way of looking at the latch data. Let's take a look at the Dragster game in the emulator. All right, so this is just a screen cap of the RAM locations, when you're in the attract mode. Let's go to our hardware here, switch it on, reset our RAM, clear our screen, and then we'll take a look at what we got. Hey, this is looking good. Yeah, you can see a lot of these things are in the same position. So like at 8.5, we've got FF. We've got some numbers in OE and OF. Yeah, OF should change. Yeah, player number, that's cool. We can see our system timer going here in 0, 1. The Stella emulator labels it based off how it is actually mapped in memory, but it's all in the same order. See how in this one, 8, 1 just increments? See that? So that's basically the frame counter. D, E, F, then it will roll over. Cool. So we could either use that or the active player number to tell when a frame is changing. Cool. Let's try something else. Let's start up the game. All right, so I've got the game running, and let's just take a look at the time. Yeah, we can see it here, the 2 times. So 4 seconds, 47 tenths of a second, actually 47 hundredths of a second. Yeah, let's just do this. Oh no, I blew up my car. Okay, I'm gonna start over. I'm putting in my own sound effects. Okay, so the time is 6 seconds, 88 hundredths of a second. Okay, we can see the 6 there. The 88, I'm not seeing it. That's a little iffy. But we can see some other things like this is the gear we were in, 4th gear, our distance traveled, and the time of both players. This is looking pretty good. I think what I'll do next is I'll go over to my code here and I will basically see if the frame counter increments. And then when it does, I'll do some additional things. Like I could have it print out the current status of what's going on in the game. And that will give us a better idea of how close we are to getting the actual values. But it's looking a lot better than it was. Okay, there's a little weirdness here. 12 seconds, okay, 12 seconds. And then B5 hundredths of seconds. Now this is BCD, binary coded decimal, so the number 75 on screen should look like 75 in hex. B5, maybe there's something messed up. Hex puzzle to the rescue. Okay, let's type in B5. And what's the difference? B5, and it should be 7.5. See this? Flipping those two switches, that tells me I have a wire transposed. Double check. Oh, sure enough, the data line coming from the Atari, D6 and D7 are switched around. Thanks, Logic Hex Game. I'm gonna try this again. Ending time, 688. Dump RAM, aha, 688. Oh, that also fixed the issue with the distance indicator. Flip those wires around, it's now working perfectly. Karen, I did it. I managed to get the RAM to copy onto a microcontroller.
Woohoo! Now, I know you weren't the most confident when you started this, but it looks like you got it working pretty good. Good job, Ben.
Thanks. Well, the thing I was doing wrong originally was I was just trying to directly read the data and address lines. Now, it wasn't that the PIC wasn't fast enough to do it. I mean, it's like 66 times faster than the Atari. However, the problem was the PIC didn't know when the address and data were actually valid.
Oh, okay.
So I had to go in, look at a 6502 CPU timing sheet, then analyze the increment and decrement instructions that caused a double write to the RAM, and then add circuitry that would accommodate for that and actually basically count a certain number of periods, and then set a flag that said, okay, now the address or the data is valid, and then it would create a rising edge, triggering an interrupt on the PIC32, allowing it to load the valid data.
Whew.
So it was loading data before, but it was not valid. So by using this external circuitry, we could analyze the waveforms coming off the CPU and basically figure out the best time to send the data to the PIC.
Cool. So now that you have this complete, in a future episode, we can have the game almost play itself and try to achieve what would be like a perfect game.
It won't almost play itself, it will play
Okay,
itself.
well it will play itself.
Yeah, so I mean, what we can do is we can take a controller. It'll basically, we can make the PIC32 act as a controller, sending inputs into the system and then analyzing what happens in the RAM and then making the fastest decision possible based off the contents of the RAM. I mean, you could also do that with an emulator, but we want to try it with real hardware just to be sure.
It's more fun with real hardware.
Yeah.
Do you have any stories about video game records? Tell us about it on the Element 14 community on element14.com/TBHS.
You can also go there to read about other upcoming episodes, builds, and special events. We'll see you next time. Hey, I used to be able to beat Contra on the Nintendo without dying.
What?
Yeah.
I once got like 5 stars playing Heart Shaped Box on Guitar Hero on like hard.
Hello. Is there anybody out there? Today's question on the Ben Heck Show, should the group Roxette come back? Let us know in the comments below. And if you're not sure how you think about it, just listen to your heart. Remember like Juicy Fruit song? Juicy fruit is gonna move ya. It's got the taste that gets right to ya. Juicy fruit, the taste is gonna move ya. Just like we build excitement, Pontiac. Now it's we build nothing, Pontiac.
Time to get back to the super glue gun.
Now in previous episodes, we worked on all the individual parts and mechanisms within the super glue gun. Now it's time to bring all those things together and make a cool, cohesive prototype. The Hyperloop is the future of loops. My name is Elon Musk, and I want to die on Mars.